So thank you to everyone for introducing nonlinear and some of the steps you can measure. So this lecture will be more about how to calculate nonlinear optical properties with Yambo. So my objective would be that after this lecture, you should be able to kind of explain what is the procedure used by Yambo to calculate nonlinear optical properties. You will know what are some of the main assumptions and approximations used, and also recognize what are the relevant numerical parameters. Of course, that will also be the object of this afternoon second tutorial on nonlinear optical properties. So let's start with the first part, and it won't surprise you. Just starting from what is the main quantity that we calculate. So what is our target quantity is the time-dependent bulk polarization. So it shouldn't be a surprise after the talk of Eleonora and also the introduction on real time from Davide yesterday. So the polarization has been yesterday introduced by Davide from Maxwell equation, and is measured as from the current. So you just take the average current density of a sample, you just integrate over some time, and then you have the different polarization between the two types. So one thing is how to calculate bulk polarization. Of course, if you have a finite system, just say an atom, you apply a field, you will have a change in the density, and then you integrate over the whole space the change in the density times the position operator, and you will get the polarization. However, what about the bulk polarization? First, of course, let's remind how from the polarization then one gets the nonlinear optical properties. This was shown schematically by Eleonora. So here I put all the time integrated. So I'm working, I see time, and then I just put all the time integration. So that is quantity, so this is the linear one, the second, the third, and then Eleonora shows some of the properties that you can get from the second and the third. So I would focus in this talk only on the predictive approach, so only on how to extract those optical nonlinear optical susceptibilities from the polarization. But again, how we calculate the bulk polarization. So one can just examine some proposal. So the first one would be similar to what you do on a finite system. You say, okay, actually your sample will always be finite. So why you cannot just integrate over all sample and then take the divide by the volume of your sample. The problem with this approach, if okay, of course, if you have boundary conditions, this will just give something infinite because you are replicating your unit cell in infinite time. If you have a finite sample, still, this won't give the bulk polarization because you will have contribution from the surfaces. So that contribution will be just into your polarization, and you want to have the bulk polarization, where you will have the bulk polarization plus this contribution, and this contribution depends on how you terminate your sample, your surfaces. So you say, okay, actually we have a unit cell, so I can take the same approach, but just transferring the unit cell. The problem of this approach is that it depends on how you choose the unit cell. So you can understand this, say, one-dimensional ionic crystal. So if you have plus minus, plus minus, plus minus, plus minus, it's very easy to see if you take the unit cell in one way, you will have polarization pointing on the right. If you take the unit cell on the other way, you have it on the pointing on the left. So this is a simple example, because if you are in 3D, it's even more complex. The other, say, okay, I can just use the continuity condition, but this will only give the microscopic contribution. So this not the microscopic contribution that we want. So how is actually calculated the part polarization? So for the moment, let's just forget about the time dependency. So this was set in the 90s by Resta and Barneveld in the theory of polarization. So they just this, okay, here I'm in 1D, but it's just generalizable in 3D. The polarization is just taken as the integration on the periodic zone of this this object here. So maybe it may seem a bit strange, but actually this it can be seen as a dipole, but it's just a moment generalized dipole. The whole problem, as some of you may know, that because the position operator is so we are using periodic boundary condition, and therefore the position operator is not well defined. So we can just then generalize and use this momentum operator just to get the dipole. If you go in discrete, it looks much since this quite ugly expression here, and then you have to you will have to calculate this overlaps. So this is just the overlap of the block state at some point and the block state at the next point. Then you have to just go through the whole line of k points and multiply this, take the logarithm, and then you will just. So I'm not going through the derivation, but how to just convince you, at least in the continuous part, that this makes sense as an expression. So it does some the theory of polarization and some limitation. So first of all, it's adiabatic. Then, in contrast of this sketch here of this schematic, it is only valid for zero fields, and the reason is that they have to use the block and the periodicity. So they assume zero field, and they usually use this expression to calculate the polarization in ferroelectrics or piezoelectrics. And they also assume that we are in an insulating ground state, meaning that we should have a gap. Of course, this is a bit limiting, especially the first two. I mean, we can survive with insulating and at least just looking at the electrics. But of course, you want, if you want to do some real time, as was shown by Davide yesterday, you need a field, and you will not be in an adiabatic situation. So in 2004, it was this seminal paper of Sousa and co-workers that, in fact, extend the theory to the non-adiabatic case with in presence of time-dependent electric fields. Basically, they show that they use the fact that the polarization is derivative of the current, and they show that if they use this expression, so you see it's the analogous of this one, but rather than our equilibrium, I'll say, block state, we have some coherent block states that comes from the solution of this Schrödinger-like equation of motion for each state. Where here we have some effective Hamiltonian. I will just come back to this later. And then we have a dipole operator, which is consistent with periodic boundary conditions. So basically what they show is that when you take the time derivative of this polarization, you get exactly the current expression for the system. So before that, also to notice, so yesterday we were introduced the real time within the density matrix formalism. So this coherent block electron that are the solution of this dipole operator, they are linked to, so at each time t, they will give you the density matrix. Of course, you just, this is the Schrödinger equation, so you don't have the terms that can just lead to the dissipation or the phasing, at least not in an ab initio way. Okay, so this has just removed the adiabatic and zero field. Still, you have this insulating, so we have to start in, if you want to use this theory, from something that in the ground state is insulating, so it has a gap. It's when it's just evolved in time, according to Sousa, you can just keep this insulating, but in a 1 year way, in the sense that the 1 year should be, the 1 year state should be localized. So you should be able to get 1 year states from your system. If not, of course, the old theory is not valid. So this is just a limitation of this theory. Okay, so now how is the procedure then to calculate nonlinear optical properties? So we want the key one we want to calculate is the polarization. For that, we need the coherent block states. So then what we do in Yambo, we integrate the equation of for this coherent block states, and I will just discuss the effective Hamiltonian later. So what we need then to input to Yambo, first of all, the electronic structure that we need to set up the effective Hamiltonian, and then the field. So this is very different if you are used to do some calculation of the susceptibility direct of the susceptibility using response or in that case you don't have a single field, but you just have mathematical perturbation that goes to zero. Here, we need to define the electric field. So again, the procedure will be you start by defining your field by giving the front structure of the system that you calculate with EFT, and then eventually you can put also GW correction into it. Then Yambo will integrate the equation of motion. You get your polarization, and then the susceptibilities you will get by phosphorus-sensing signal. And we will see this in some detail later, or maybe not. Yeah. So, which experiment we can simulate? So the nice thing of real time is the flexibility of it, and so you can really define your experiment. This part, which is the part you don't want to touch, you don't need to, it's there, but then you can change your input field, and you can change how you process your signal, which is very easy because you can use Yambo. And then you get different experiments. So the first thing you can do, and this is the first tutorial of this afternoon, is just get the dielectric function. For this, you just will hold a key to your system, you integrate, and then you will get polarization. So this polarization will contain, so you get the system. So basically, you excite all the high frequency of the system. So this is the polarization that is mixing all the eigen frequency. Then you take the Fourier transform, and you get the electric function. So the imaginary part will give you the absorption. Then you can also do some different experiments, like so the second or third harmonic generation that was introduced by Eleonora. So what you do, you just take a monochromatic field, again you integrate, and then the polarization will look very much like monochromatic, but actually it has very small contribution from all harmonics. You cannot see because these are, so the second harmonic is 10, is the 6th order of magnitude smaller, and the third harmonic is 12, 13 order of magnitude smaller, so you don't see it, but you can extract again by a finite discrete Fourier transform, and then you will get the second one, the third harmonic generation. Fourth is very difficult because of it's very tiny and it goes into the numerical accuracy of the content. Just this is also connected to what was presented by Eleonora. When you get 7 harmonic generations, so you will get this susceptibility, but take care that it's not, the susceptibility is not what is measured in an experiment. In an experiment, you just shine a laser, and then you just collect the signal, and then what you have is your intensity. So you just can have a filter, so you have the intensity at 2 times the frequency of the incoming laser. This is what you have. So it's not, you're not measuring, it's not a direct measure. And then you need a model to extract the chi2. And this can make quite a difference. So there are some groups, and that was this the origin of this huge difference that was shown by Eleonora, that takes a 2D material for which you would need a sheet model, and then they apply the bulk model, and then can get some value for chi, which is 100 times. So be careful when you compare this with the experiment, and be aware that they are not measuring this directly. So when you read the paper, try to see how they extract the, or when you talk with your experimental partner, how they extract the Chi2. So another thing that one can calculate, for example, is the intensity dependent refractive index or two-point absorption. So you can do the same experiment as for the second harmonic, third harmonic, and so on, but you will vary the field intensity. Then you can use some extrapolation to get, for example, to get the third contribution and the frequency. So in this case, you're not taking the third, the chi3 at 3 omega, but the chi3 at omega. So that's fine. Okay. So you are taking this contribution. Actually, you have also contribution from the fifth, from the seventh, and so on. So the type of experiment you are addressing are just this kind in which they shine a laser and then they focus the beam on the sample with the lens. But because it's just a focus, if you move the sample slightly, it will just experience a different intensity, and this will just change the higher order of the polarization. Of course, at maybe you won't say and you won't see anything, but then if you can extract using, for example, this extrapolation at different fields, and then you can just find this third contribution to the intensity. Then is something very recent. We found is just so you can of course have two-color laser as an input, and then you can look at how the frequency of this sum or the difference, or you can also look at something like field-induced second harmonic generation with a by a terahertz field. So this works again the same for the integration, and then all the work that we did in this paper was just signal post processing, which is was quite a work, quite efficient. But we have found a couple of actually mathematical equivalent way. One is using square minimization, and the other one with signal value decomposition. So you can look at the details in this paper. So the one one can look at terms of frequency. So in this case, you just have two colors, and then the output signal will just have the sum of the difference of the two frequencies. Or you can also look at third order approaches in which, for example, you just pump one laser and then you look at the 2 omega. And the second laser is at terahertz, so it has a frequency which is much smaller than the incoming optical laser. And then you can basically, this is negligible with respect to omega, so you have a second harmonic induced by this applying speed. So you can take a centrosymmetric medium, put this field, it will just break the centrosymmetric symmetry, so you will have not zero second harmonic. So let's come to assumptions and approximation, part 8. So first of all, of course, there are the one for the effective Hamiltonian, the many-body effects that you put in. And so here just I put to this something that you should hopefully remember from yesterday, was presented by Davide, so we have, let's say, the same freedom of choosing these terms. So if we take just the Hamiltonian at zero field and we propagate, we will have the same as independent particle. So here is the absorption of the independent particle. So this is for a 2D hexagonal nitride. So you have this Farlow singularity. This is the same replicated at half of the frequency, and then this will be the second harmonic eurodome. If you add the R3 potential, so the R3 potential will change with time because the change in the density. So actually, we know that mostly local field effect doesn't have a lot of effects in homogeneous bulk or homogeneous systems. In thermal iteration, because it's very sensitive to the field, you see here this green local field effect. Then we can, one other thing we can do instead is to add particle refraction. And if you look at the absorption, it's just shifting spectrum, but it's different in the second harmonic generation because you are mixing the poles at second and first order. So you will see a strong renormalization of the peaks, and you may also have something where you have resonances between pole at first and second order, and so you have this peak up in here, which you wouldn't expect. So it's not a simple shift. And then finally, we can have all contribution together and just have the same as the equivalent of the band salpeter for the electric function. So this is just strong epsilons in the hexagonal boron nitrides, and these are just replicated at 2 times the boron. And then you see the second harmonic generation indeed as resonances with epsilon and 2 photon and single photon. So then another assumption is that we are using classical fields. So we are simplest are semi-classical because we have quantum for the electron, but the fields are treated classically. And then we use the dipole approximation, which you could have guessed by the fact that here I want just the electric field depending on time. So in electromagnetism, you will have propagating electric fields. We use the dipole approximation, and the basis is that the unit cell is much smaller than the wavelength. So this because we are we go from infrared to ultraviolet. So we go from 10 micrometer to around 100 nanometers, and our cell is just a few angstroms. So the dipole approximation is valid in this region of the electromagnetic spectra. So what is the effect of this approximation? Well, the effect is that you cannot describe the propagation of your field. So this phase matching that was discussed by Leonora is something that you can't capture, but what you can capture is the effect of the field onto your system. So finally, which this is related to also our today tutorial, is the parameters that are important in a real-time simulation. So first, the parameters that for the effective Hamiltonian, this will be the same as you have seen yesterday and the day before. If you have to convert the GW, if you have to convert the best bidder, they are exactly the same parameters, so I'm not going to do it, but you have to just convert them carefully. So usually you will do a linear response, so you calculation before, so you will know already those parameters. Then you have to calculate the value phase at the combined dipole. So if you remember in the discrete expression, there was this, you have to have this overlap at k points, neighbors k points. So basically you are doing a numerical derivative with respect to k. So this should be quite dense. So you have to be careful and converge on the k-point mesh. Then, of course, you have to integrate the equation of motion. So you need numerically. So here you have to define your time step. It is usually defined as 10 attoseconds, and it's quite good, but you have to, in principle, verify it's fine. And then if you have monochromatic signal, the simulation time is important. I will explain later that we need to introduce the phasing factor, and so depending on this, the phasing factor, you should wait before you do your Fourier transform of the system to get the harmonics. So let's see some details in the calculation. So first of all, the very phase polarization, you need dense k-point mesh. So here are some calculation on a 6 by 6 by 1. So in gray, you have the linear response. So this is just linear response. And then you can just do with the delta kick in real time, and you see that you don't get the same results. And you say, wow, what's going on? Actually, the problem is that 6 by 6 by 6, your dipoles are not very accurate, and the error is that. So if you go to 48 and 48 and 48, you see that you are really on top of the linear response when you do this real time. So actually, this is a good practice to choose which is your k-grid. You can do a linear response calculation, and then you do the real time with the delta kick, and you try to 5 minutes, okay, and you try to see the differences and you to converge your calculation. The other one is the time step. So here, just to see the effect of a time step which is too long to iterate your equation of motion. So you have it again in blue here. You see that if you not converge, you can get some error in your spectra. This is the second one generation. And then also, if you have a monochromatic signal and your simulation time is too small, you will observe this oscillation around the correct value. So how these are coming from? So basically, when you give a monochromatic signal, we cannot just switch it on at minus infinite time. So we switch it on at some time. And this switch on is just it's a small delta key. And with a small delta key, you excite all the system high frequency. So this will be very small because the delta kick is small. You may just have a soft sign that just switch on the sine signal very slowly, but nevertheless, you don't see it. Well, you may see it at the start, but they are always of the some order of magnitude, which is competing with your second harmonic or third harmonic signal. So basically what you need to do, you apply phenomenological phasing, and then you just wait that the eigenfrequencies are just negligible with respect to the signal of interest, so second harmonic and third harmonic, and then you then take one period and you sum after sometimes, and then you sample your signal there. So now let's see if we got what we wanted. So I asked you. My objective was to do some. So P1 is calculated by Yambo to obtain non-linearity properties. What
was the try?
Go on.
What would you need to extract the optical property?
Polarization.
Polarization. The theory of path polarization is an expression which takes the form of a dots phase. By phase, yes.
Well, not sleeping.
The dot approximation is the electromagnetic field as a uniform over the size of the unit cell dipole. And finally, a relevant numerical parameter to integrate the equation of motion is the time step. Thank you very much.
Thank you very much. That was very interesting and on the talk. So now the session is open for questions. Yes.
In the polarization approach that you discussed in the previous slides, that is implemented in the Yambo code, able to explain the spin selective excitation materials.
The spin excitation, you mean?
Yes. For the polarization approach.
Yes, I mean, if you have a spin, if you put the spin your calculation explicitly, yes, you will have spin. So I do everything just without spin, but your chi, I mean, if you have different spin, it will just be into your chi. So that starts.
I mean, if I can give a general answer, the way Yambo enters the speed is modeled through the shape of the wave function from the Gaussian calculation. So it is those spin polarized of the spinos. And then once you have that, it enters in the integrals with the basis method, and the spin is applied for.
So basically, for analysis, we will be able to control for each spin-up channel separately.
If you have a spin polarized calculation, yes.
Yeah. So you should have a spin polarized, and then all this will just have sigmas, and yeah.
So thanks a lot for the discussion of the definition of polarization. So I'm wondering, typically the literature presenting those definitions all tend to make reference to non-interactive. So you have the orbitals, can the theory be extended to a description if, for instance, interactive wave function dies on orbitals instead of regular normalized orbitals?
So I skipped one part where how to get to this. So what you in many body, what you will have the many body wave function, and then the operator will be an exponential of the an expander with the fate will just have the position operator, and then you take the logarithm. And you need indeed to get this expression a non-interacting or effectively non-interacting system where your many body function can be represented by Slater determinant. Thank you very much, because this is another restriction. So we can have something like the clean exchange, because we still have a representation as Slater determinant, but as soon as you will have something different, more many body, I would say, then you can use this expression.
Thanks a lot, because this is one that I've been thinking about quite a long time. I think I've seen in the literature some let's say consequences of this that are in dynamical midfield. I think the find a very issues in defining the LO splitting with the components, because that depends on the basis and with the dynamical potential. Basically, they mentioned that there's still an open problem. They don't know what to do. And I think the problem is exactly.
Yeah, it could be that. I'm not aware of this work, but I guess that it's with dynamical midfield that depends on the frequency.
And I think also I've seen people trying to massage the theory to compute some invariants. Again, with derivatives, again, in the presence of the interactions and dynamical, so that computing some certain invariants in dynamical. I think the problem is still.
Yeah, but we are in a still the same ground with this clean exchange. Luckily, yes. Thank you.
The question.
It wasn't really clear to me if you look at tectonic effects in this effective Hamiltonian, how do you do it? This is formed two particles like tectonic and capital that we were discussing yesterday, and you have to solve it like at each time. You have to repeat this calculation at each time of the.
Yes. So if you do, depends on the experiment. So this experiment, yes. So you have a monochromatic field, and to get this spectrum here, that let's go down, goes over several electron volts. For each point, you need to just repeat the experiment. So you just need the. So how we introduce the Benson feeder is just putting the self-energy, this exchange self-energy that was introduced yesterday. So I went a bit quick on that, sorry. But basically, this just is the screen exchange self-energy, so which correspond then to the W capital when you take the derivative, and this is what, when you just evolve in time, gives you the exotonic effect. Sorry, I don't have the expression here, but it has the screened exchange, and then it evolves in time because, of course, it depends. So so this will be the density, and this will be the density matrix. So the density matrix changing in time, and that's how it evolves in time.
Okay, so if there are no other questions,
The computer is based on the simulation or taking into account
Oh, so the go back.
Yeah.
Thank you.
Yeah.
Yeah, so this one is just calculated at the start, so it's part, let's say, of the equilibrium one. And so if you look at this paper, we show how actually, of course, this is dynamic and this is not dynamical, but basically this is a difference between the many-body effect at time t and at the start, and this is how this just cancels out.